Yeah, thanks a lot for inviting me, for having me here. And I think you can tell that you are in a cool research community if you can see slides with list code on it. And I think that's kind of very cool. Yeah. So I'm very interested in, I see kind of a driving force for cognitive capability in agents to be goal-directed object and goal-directed manipulation of objects and substances. I think that's kind of one of the tasks where cognitive capability really had to evolve in order to kind of deal with these tasks. And the kind of problem that I'm really excited about and that I want to understand is the question of how can an agent take very underdetermined, very vague manipulation task requests such as clean up, set the table, bring me something to drink, and map that into a body motion of a robot, right? And in a body motion that achieves the desired effects and avoids the unwanted ones. And I think that's kind of the key challenge for robot agency. And the way we approach that problem is that we want to do understanding by building. So we want to have computation model that can generate kind of behavior that satisfies this task. And a challenge task that we basically have selected is what we call the EASE household marathon or household challenge, which is basically a day where a robot has to set the table, clean the table, load dishwasher, unload the dishwasher, and in very simple tasks, prepare some very simple meal. And we would want to do that task kind of for long times. We would want to do it 3 times a day and for kind of 5,000 days or something like that, so that we can collect the lifetime experience of a robot doing these tasks. So if we give the robot a task like set the table, so this should happen, right? So the robot should go there and pick up the object and place them on the table in the arrangement where they are supposed to be. And the big question is, right, if the robot is executing a loop and it's always executing the action, take an item that is missing on the table, fetch it, and place it where it belongs. And all the other behavior that is very context specific to that task and has to be inferred from the knowledge of the robot and the reasoning capabilities of the robot. And the question is, of course, how is that possible? And if we want to generalize even more, we can basically go for assembly tasks and other things. So the way we set up this problem is that in our framework, which is kind of the cognitive architecture CRAM for a cognitive robot abstract machine, is that we equip the robot with generalized action plans. So for instance, a generalized action plan for the task, fetch and place any object from any place to any destination. And this plan essentially tells the robot, in order to fetch and place an object, you should go where you believe the object to be. You should position yourself such that you can see and reach the object well. Then when you're seeing it, you should take the appropriate reaching and grasping motion and pick it up at the proper holding position, then go to the destination and place it. So this is kind of a very generalized action plan. And this generalized action plan is coupled with kind of methods for generating motion plans. And motion plans have schemas. So for instance, for putting down an object, you have phases such as reaching for the destination, or kind of picking up an object, you reach for the object, and you basically have to grasp it. And for each phase, you have motion parameters. You can decide on which grasp type to select, where to place the grippers on the object, and how much force to apply. So what the robot control system has to do is it has to bridge the gap between that generalized action plan and the concrete parameterization of the body motion that the robot needs to execute in order to accomplish that task. This is done by a process that we call contextualization. The robot takes its model of the current scene and the underdetermined instruction and derives the parameters of the motion plan. And in order to do that, the robot has to apply its knowledge and its reasoning capabilities. There's no other source of knowledge where it could possibly accomplish this task. So one way of thinking about that, we could actually think of that contextualization process as a function or mapping that takes the object, the task context, the environment, and the scene context, and maps it to behavior patterns, right? And then we would actually do what people in machine learning do. We could try to approximate that function using deep networks in order to accomplish the task. We are not going that way, but we rather kind of try to apply a combination of machine learning techniques and more traditional symbolic reasoning techniques from AI. And the reason you can see if you're looking at that problem, right? So you have an underdetermined task request, pour the water out. You kind of have a pot with water and vegetable in it. And any system, any robot system that can, that is able to accomplish such a manipulation task successfully, I think has to make the inferences that it has to grasp the pot by the handles, hold the pot horizontally, tilt the pot around the axis between the handles, and hold the lid while pouring. So in order to do these tasks, it's actually a kind of a promising approach is that we are taking generalized modular action knowledge chunks. We compose them on the fly as we need them. And those combination of knowledge chunk, they give us sufficient knowledge about how to perform the right motion, even if we are far away from the examples that the system is trained for. So we are basically proposing a cognitive architecture that does that. So the working horses of the cognitive architecture is the plan executive that executes the generalized plan by parameterizing and executing the motion plan. And the second component is the knowledge representation and reasoning system. And the plan executive, it looks at the generalized action plan and the way the underdetermined actions are described at the respective time. It looks at the parameters that the motion plan requires, and it then generates a query. It basically asks, what motion parameters should I set in order to achieve that underdetermined action? And this query is basically sent to the knowledge representation and reasoning system, which is responsible for giving an answer, which is kind of a parameterization of the motion, which can be executed in the motion plan. And in this talk, I will mainly talk about the knowledge representation and reasoning capabilities that we need in order to do that. So just to give you an idea that indeed we are talking about a hybrid representation and reasoning problem. So we basically had a controller, kind of, it was very much the one you have seen in the video, with a hand-coded knowledge base of the knowledge chunks like the ones we have seen for the pouring case. And this hand-coded knowledge base is sufficient basically for generating of a kind of setting the table. And it basically generates, but it also generates a lot of backtracking. So kind of solutions that it suggests turn out not to succeed. We can improve the performance of the robot control system by adding different kinds of reasoning capabilities. So for instance, prospection. So we can basically let the robot predict whether, for instance, kind of a particular pickup strategy would allow it to place the object later without having to recasp the object. And we can show that essentially adding prospection will substantially improve the robot control system. The same is for experience. So if we get all the experience about which of the parameters actually succeed and which ones fails, we can use that and learn from experience, and we get a better control system. We don't have to learn from the robot control system. We can also learn how to parameterize the motions or other background knowledge by observing humans doing the tasks. Kind of the advantage for that is that knowledge acquisition is very efficient because humans apply their common sense knowledge in order to choose the right strategies. The problem is that we have to transfer kind of what we learn from the body of the human to the capabilities of the robot. Kind of another way of improving is changing the control structure of the whole plan. So for instance, instead of transporting objects one by one, we can also have a transformation to use a tray and then first put all the objects on the tray and then kind of transport the tray. So the challenge, which is kind of the challenge for also for my future research, is that I would like the robot to learn manipulation tasks by reading instruction text and watching instruction videos. And this is kind of, and thereby basically kind of learn manipulation capabilities, for instance, pouring or wiping in an open domain with different tools and at different circumstances. And that's kind of a very complex learning task, which is much more problem-solving task, as for instance, also looked at in interactive tasks. And so we have to learn the task. We basically have to extend the model. We have talked about causal models, but also models of the control system that allows to extend the predictive capabilities of the robot. And we have to learn how we can improve the task performance. And I think this is interesting because I think this, if we are touching this learning task, we are learning in a very open space, and we have to basically learn with very few examples in parts of the domain where we haven't had any experience before. So instead of kind of learning that just from data, so what we think is that the heart of the system should be kind of a predictive modeling and knowledge representation engine. And by that, we mean that essentially we equip the robot with an inner world model, which is essentially a game environment in which it can emulate everything that it does in the real world in its own environment. But this environment is not only kind of a game environment or virtual reality environment, but all the entities in this environment are axiomatized in an ontology, which is, essentially makes the whole virtual environment machine understandable and gives everything a semantics and background knowledge. We also use the data structures, the virtual reality scene graphs, to model all the entities in the world at varying levels of detail, in particular also sub-symbolically. The whole engine is wrapped in a logic-based language, in a prologue language, so that the predicates are, or most of the predicates are defined with procedural attachments, so that the truth values of the predicates are computed on demand out of the data structures of the virtual reality environment. And that's kind of system that we want to go for. So the knowledge representation system that we are thinking of is a predictive modeling and knowledge representation engine that can imagine, model, represent, explain, predict, transfer, and plan underdetermined action descriptions and their execution based on an inner world model and in a machine understandable manner. And by machine understandable manner, I mean that we can formulate queries in a logical language, and the system is able to do open question answering. So I will basically talk in the remainder a little bit about the different parts of the system. So the interface layer is a logic-based language, time interval logic language with predicates, holds, occurs, and entity. And it allows us to ask queries like, we basically want to look for a spoon that at the beginning of an action is on top of a table. Or here's another example. We basically look at an action of the type putting down, and we want to basically look at the time interval in which this action took place. And we want to look at the trajectory of one of the hands in this time interval. And we get a sub-symbolic data structure, namely the data structure that we can use in the system using a symbolic query language. So important is that we want to have symbolic reasoning because we want to represent knowledge through modular, composable, and generalized knowledge chunks. And we also want to basically compose them and just search for answers for motion planning problems by basically searching for simple structures that solve a given problem. So one of the problems that we have if we are on a robot is that symbols in symbolic representations are too abstract. So they don't suffice for generating the motions that a robot has to execute. So what we are doing is we are taking the atomic symbol names and we link them to the data structures in the virtual reality graph, which has enough detail to visually render kind of the scene in using the data structure or to simulate what it's doing. And another advantage, if we are going for an implementation basis for knowledge representation using virtual reality simulation techniques, then we have a simulation and an imaginative reasoning component as additional reasoning capabilities. And we can manage and maintain the detailed models by basically, we can update the belief state of the robot by rendering the current belief state and doing pattern matching with the image that the robot is capturing, which means we can solve it through machine learning based techniques. We also use the system in order to cast the whole knowledge structures as symbolic representation, as symbolic knowledge base. So if we basically have models of all the relevant entities, then we can generate the scene graphs completely out of symbolic knowledge bases. And we can exploit physics simulation and rendering as additional reasoning mechanisms. So for instance, we can basically define a predicate expected image, and we can use the rendering image to generate the data structure that the perception system can work with. Or we can build an ideal segmentation of an object in a scene by just asserting that all other objects in the scene are invisible and only the interesting object is visible. So let me just show you what the system is capable of doing. So in the upper part, you see the symbolic belief state of the robot, and in the lower part, the real world situation. You see that the object is the robot is updating the belief state. It's using kind of the segmentation capabilities to interpret what it's seeing. It can answer all the questions that we have seen that are needed for parameterizing motions based on using symbolic queries based on this kind of knowledge base. And you can also see that the robot can infer with a belief state things that it couldn't see. For instance, if it lets the object go, it knows that it's dropping on the floor. And so it's also training its perception system using its inner world model. And we can also use the simulation of plans in order to do dreaming and learning in times where the robot is idle. Just the last video. So here we see how we take the belief state of the robot and assert it as a virtual reality scene. We then ask a human to accomplish a certain task, such as setting the table, and inside the inner world model, we can interpret the activity of the human by detecting the force dynamic events such as contact hand object and lifting from supporting surface. So we can have a parser that passes on the fly the ongoing activity and generates these kinds of representations of the action. So we have segmentations of motions into motion phases. We can see where the gaze is looking by performing action. We see the trajectories in which objects are taken. You see that there is a cool combination of symbolic and symbolic knowledge structures. Okay, so the kinds of things, and I hope I could motivate them a bit, is that action execution is not an application of knowledge representation and reasoning, but its purpose. So if a knowledge representation and reasoning system cannot define the actions and the motions that a robot can take, for a robot, that kind of representation is pretty useless. The goal of knowledge representation and reasoning for robots must be the design and the understanding of machine understandable predictive modeling engines for action execution. They must the purpose is to avoid catastrophic failures and damage in execution time. And for that, we need a very powerful predictive mechanisms. And the third lesson that we have drawn is that the disruptive advances in game engine technologies, machine learning, hybrid knowledge representation, and data science make this kind of research agenda feasible, and we hope we have some success in pushing the manipulation capabilities of robots along this line. So thanks a lot for your attention.
Thank you so much for that great talk, Michael. We very much appreciate it. Very interesting. We have a whole lot of questions. I think the first one is from Romy Bundry. And so the question is, should an embodied system have a module that models or encodes intuitive physics associated with objects in the real world? That is, how realistic does everything need to be?
Oh, yes, I think definitely it should have. And I think that the requirements for accuracy are completely overrated. So I think the biggest problem is not that the simulation is not good enough. The biggest problem is that the robot doesn't know the physics parameters that it needs for doing the right simulation. So for instance, if you're pouring some substance, you don't know the viscosity of the fluid. But that's the same problem for humans doing these kind of things. So we have to find ways of how to kind of use simulation, mental simulation, as an information resource without being kind of a slave to the prediction that it makes, right? And I think the mechanism is kind of the tool that we have is what the robot control system does with the simulations.
Okay, thank you very much. And another question from a couple of people. Natalie started this one is, how do you store precise information required to simulate the world in the symbolic knowledge base?
Oh, it's basically the precise knowledge is all virtual, right? So you have basically attached with the symbolic predicates a procedure that computes the truth value or kind of the parameters for which the predicate is true. And that's actually retrieving symbolic information out of the data structures or out of the computation that the virtual reality scene graph is having, right?
Yes.
Does that make sense?
Yes, yes, it does. Thank you very much.